Okay, yeah, so thanks for introduction. Yeah, I get that a lot. My name is hard to pronounce. I'm Laurynas Dagys, as originally pronounced, but that's all good. So like many of people here, I'm representing University of Southampton, which you can see in this lovely picture here. And I'd like to present our project, our work that have been doing just recently and has been just accepted today. So it's quite fresh project, fresh results. So the title is GemPHIP, accumulation of singlet-order and methylene proton pairs. And let me start with the motivation of why do we do this this project at all. So maybe point. Okay. So it's somewhat related to what Malcolm said previously. It has this virtual triangle. So there are three things that we try to combine. So we have methylene group, we investigated CH2 group, which obviously have highly correlated proton spins and due to their close proximity, and therefore singlet state lifetime may exceed a lot the lifetime of magnetization of those protons. And well, parahydrogen polarization is a unique method that can supply with singlet state. So we try to combine all of these three and to see what sort of effect would one expect. So, well, obviously you all of now know that this is just a slide that I would like to show that how beautifully these things can be connected. So, so there's cis-trans conformations, and also there's geminal positions that say two atoms can attain. But something nice that unifies these things, and these are just examples. So malate, fumarate, and this gem product with question mark, and element of ruthenium is the one that combines them all somehow. And what I mean by that is if one uses this precursor that I've shown you here is the dicarboxylic acid, and bubbles with parahydrogen or hydrogen and with a catalyst, then we can produce malate, fumarate, and this weird gem product. So for instance, note this regular 1H spectrum at 9 Teslas. So this has been just this precursor bubbled with hydrogen, and this is what one would get. So clearly we see some fumarate malate peaks appearing, but also we see this peculiar pattern due to methylene protons somehow. And there's the rest of the peaks, which are solvent impurities, succinate, catalysts, and other impurities. So we thought that this pattern is quite interesting, and that has been observed by Barbara and James, who just talked just previously. So the reaction of that is not straightforward. So if one would hydrogenate this precursor with hydrogen, one would get a mostly fumarate, but then apparently there's a side reaction that we can form side product, but it requires additional precursor here. So then it cycloadds on this ruthenium catalyst, and then we form this sort of furan derivative with these methylene protons positioned here. And this reaction is not as straightforward as it looks like, and it was investigated quite extensively by Markus Leutsch and his colleagues in these references. And what they also shown that was quite surprising, that if one uses parahydrogen, then singlet state still manages somehow to survive this reaction. So nuclear singlet state is not disrupted or disentangled. So they've seen some presence of singlet order in this product. So we thought it's quite an interesting phenomena, and we investigated a bit more deeply. So now I start to declare certain things for later. So we have singlet order as one of the important elements, but in Zeeman basis, when we have really a lot of chemical shift difference and other, say, symmetry breaking interactions, then singlet order may dephase into also known as ZZ order, which was shown previously as well by others. And there's a couple of factors for normalization. An interesting thing that if singlet order does contain ZZ orders, not too surprising, I guess, but it also works in the other way around. So in principle, we have factors that, so if one would project ZZ order as singlet order, we would get about minus 1/2 of that, of amplitude. So we used a sequence that was published in Sarkar's paper, which in principle uses chemical shift difference and some J-coupling to transform either of these spin orders into magnetization. So for now, I'll show you 2 pulses and some delays, but from now I'll just refer to some sort of box. We call it reverse Sarkar sequence. That just, if one would feed ZZ order or spin singlet order, sorry, that would convert it into magnetization, observable magnetization with these factors. And these factors will later on will be quite important, and you will see how later on. Okay, so if one has singlet order in somehow by, well, one dissolves parahydrogen and then chemically reacts it into something else, then we clearly, in this case, we had a chemical shift difference of 80 Hertz in 9 Teslas. So clearly it will dephase into ZZ order. And then that ZZ order would also decay if that was overpopulated state with time constant of TZZ. Just as a reference, the T1 of this system in such magnetic field at room temperature is around 1 second, which isn't like a lot. So it means that ZZ order also is would decay quite fast, maybe not with the same rate, but still relatively fast. But then one may use a trick, or well, not a trick, but a technique that we call spin locking. And spin locking essentially negates or doesn't allow singlet tripling exit to happen, such that singlet order can be sustained. And then singlet order, as you may know by now, has a different relaxation type constant, which is called TS. And in this system, TS was surprisingly, or not surprisingly, a minute. Well, it indeed, because of the highly correlated methylene protons, and it's almost 60 times longer lived than just magnetization. But of course, spin locking needs some sort of optimization, so we optimize some magnetic field and spin locking amplitudes needed to avoid singlet tripling fixin. And these sort of effects has been extensively also investigated by Marina Corrette and Giuseppe Pileo in Southampton. So they use different chemical systems, but they exploited this phenomenon quite well. And then, okay, so this previous experiments were done on thermally polarized samples, so that's not too much of interest or on the basis on our project. So we attempted to do that with parahydrogen. So we bubbled a little bit solution with parahydrogen, and then waited 3 seconds for the bubbles to dissipate, and then we had some sort of variable time tau2, and then we applied the pulse sequence. And on the other hand, we did the same thing, just we applied spin locking now, such that we could actually sustain singlet order and not ZZ order and see what is the difference. So first of all, in this case, we just seen that the signal would just decay slowly. I mean, this time scale is still relatively long, but it still kind of decays. Nothing too surprising. Well, it's mostly due to the slow reaction of ruthenium with ruthenium catalyst, as James just previously explained. And then we have, on the other hand, this is a rather more interesting phenomenon. So we have a somewhat of accumulation, but then it also starts decay, but at relatively longer tau2 times. So we thought it would be interesting to adapt some sort of model to see what are the processes and what are the timescales of these processes. So for that, we need to, okay, sorry, for those that are interested in details, I'll just rather tell you what is the sample composition. So it's relatively high concentrated precursor and catalyst, and well, 300 microliters is just to put the sample within the excitation coils. And other parameters, and this picture is just for amusement, other parameters are magnetic field of 9 Teslas, temperature, and spin locking power, and the pressure. So we're working at still relatively mild conditions. There's nothing too special. But so let's see what is the model that we used in order to investigate the data points that I've shown. So in order to have singlet order in the system, we need parahydrogen solution. That's obvious. So we use bubbling for that. And that parahydrogen would slowly convert into singlet order of the general product now with some factor K. Unfortunately, in this system, there's lots of products that are forming. So this is only a fraction of that process. And singlet order parahydrogen solution will also relax slowly with RC. And then if we don't apply spin locking, any of the spin locking, then we have 2/3 of the singlet order here. And these two will decay with their relative relaxation rates. But then if we had some of the ZZ order prior the pulse sequence and apply, prior to spin locking, and then we apply it, then we can convert a half of that into singlet order back again. And then after that, we apply a pulse sequence, which just converts it into X magnetization. So clearly there's, with amplitudes of 2/3 and minus a half. So clearly there's a spin dynamic part and chemical part here. So I'll just show the equations that we used. So on the chemistry side, it's quite simplified, but because we had an excess amount of all the catalysts and precursors, we can say, okay, well, it might approximate to something like that, which is just simply hydrogen being consumed by this K total. But the useful amount of project is actually forming with this K instead. So the singlet order of the parahydrogen will be consumed then by the chemical reaction and by relaxation process. And this is important because this is what relates to now to spin dynamics bit. So if we want to see what this is the singlet order of the hydrogen, then we have this R sigma that just slowly eats it. But then if we don't have a spin locking, so we're seeing, okay, well, what is the ZZ order now on the general product? So then we have this K, which is producing this singlet order, and we convert it back to ZZ order. So we have this 2/3 factor. And then obviously it will decay slowly with this RZZ. Whereas in the other case, it's quite similar. So we don't have this 2/3 now because we're just doing 1-to-1 singlet order conversions. So that's all good. And then we have this RS, which is singlet relaxation, singlet lifetime. Okay, well, we still haven't concluded that yet because we need to apply a sequence. So in order to fit something, so we use this amplitude now. So we have this 2/3 because of how sequence converts singlet order into magnetization. And while putting things under the reg, we can actually get to this form, which is clearly just a bi-exponential form. So there's a part that says, okay, how the signal slowly relaxes and how signal slowly increases with time. Whereas in the other case, it's almost exact the same form, just different amplitude, different relaxation rate. But this is the same component just with a different prefactor because of, again, because of the amplitude reasons. And let's go with these data points, and we fitted them with equations. And then we get this nice little table, and it is nice and little because we used a global fit. So we took all of the data sets and fitted all of the curves at one instance and not separately. So these parameters, unfortunately, are not really well interpreted because, well, first of all, they don't have a good, a unit. And this, for example, even has a mutual dependency. But these are a bit more important because they actually say of how fast the ZZ order and TS are in contrast with each other. And also we have this interesting T sigma. And I'd like to underline that you may notice that this plus or minus 9 seconds is quite small, having in mind that this is only 1 point relating to decay. And I've snuck a little data set here, which I haven't told about yet, but it's quite similar to what we did before. So that experiment was exactly the same thing, just we used a different bubbling time such that we would convert everything that we could. And then we just sustain it with spin locking. And this function actually simplifies well into mono-exponential decay, and this is what we use for fitting. So these are the parameters what we get with this model, which is obviously idealized, but it's still managed to tell us a good story. So to summarize, I'd like to say that, well, germinal hydrogenation is possible using parahydrogen, which was shown by Marcus first of all. Then singlet order between methylene protons can be maintained by spin locking, which was shown by Marina and Giuseppe Pilero in Southampton. And then singlet lifetime significantly can exceed to 1, obviously, and then it may allow to accumulate singlet order if it's long enough, in contrast, for example, with other parameters like, reaction time. And we used a simplified kinetic model, which was obviously maybe too simple for the complex chemistry that is involved, but it still managed to give a sense of timescales that are working against each other or with each other in the system. And so with that, I'd like to thank the team that actually, without any of them, this project wouldn't have been concluded. So that was really, really great work. So Barbara and James actually seen those massive germinal peaks in the beginning. Marcus obviously had a lot of experience on these reactions. Also, well, Gamel, Johannes, and they helped us with synthesizing the precursors and actually verifying the structure. That was really a big struggle for us. And obviously Malcolm for supervising and providing with this idea of this model that we didn't have in the beginning. So that was a great, great use for us as well. And yeah, obviously I'd like to thank you and for listening. So if you have any questions, I would be pleased to answer them. Thank you.
Well, thank you for the great talk. I hope you can hear me a little bit now.
Yeah, I can hear you
better now. I guess we have a couple questions. One of the first ones is, can you somehow control to get more singlet order, and what does that ratio depend on?
Well, okay, well, first of all, this reaction is really not really effective. As you may have seen from the, sorry, I think it's best if I just go like this. Okay, yeah, so as you can see, this is not really an effective hydrogenation experiment, right? I mean, we're not getting a lot of singlet order, and I guess if we would want to get a bit more, then we could also increase pressure, maybe flow rate of the bubbling, and go and we'll try to get that singlet order as quick as possible. But the problem with this reaction that is actually slightly impedes the catalyst. So we obviously not gonna increase a lot of that singlet order anyway. So there's a limit. So for example, this concentration that we get in total is roughly around the amount of catalyst that we use. So there's not really a lot of ways to control that, I would say, but one would may attempt increasing the pressure and these external parameters or temperature, for instance.
Okay, great. And what other, I guess, what's the range of molecular systems that you think this work could be applied in?
Well, we first of all, that was quite a surprising system in the beginning. It's not yet, I would say it's not well designed for any application yet, because that's, well, that was, okay, so that was an effect that was interested and kind of inspired us to see what's actually happening. So it's not yet there yet to be able to apply for other systems, but in principle, one can think of ways maybe using this system and knowing that these methylene proton pairs can be somehow chemically produced by parahydrogen, and you can use enough of spin locking or low enough field. So applications may arise of that, but currently we don't have anything like, well, we don't have a lot of in mind to already apply this. So that's really like a fresh observation that we did.
Okay, that's I guess all the questions we have right now, but I'm sure if there's anything else that comes up, they can shoot you some questions in the Slack channel.
Yeah, sure, of course, no problem, yeah.
Thank you so much.